Now, what enabled us to run on AWS is that we already have a master worker parallel compute architecture. We actually were quite fortunate in our initial architecture of the underlying XWI code, in that it already runs on a schedule with a lot of different workers that could come in and out. And what we did on top of that is a cloud-native orchestration system that we had to write from the ground up. We found that even things like Kubernetes, which is very popular these days, are a bit too high level for us, because Kubernetes is designed to run on something like about 100 to 1,000 machines. But our goal, our ambition with this entire project is to be able to run this on 10,000 machines, running on 10,000 square kilometer projects. So something like Kubernetes even is very good, but it is very, very bad at handling a giant amount of machine that you want to spin up in 5 minutes and then have it all come back down. So we had to write a lot of custom code, but a lot of it is built on cloud-native architecture. And a lot of it is sort of built inside a self-contained cloud, virtual private cloud that we use on AWS to keep the data secure. And because we built all like this, we're able to enable a pay-as-you-go SaaS model. And that's just the added bonus of having things architectured as agile as possible. Now that actually required a lot of thinking about how we build the system. You can see that down here, this is the actual scientific code. That is like less than half of the overall architecture program, right? So, I mean, even though this is all where all the computational work gets done. So if you just crowd all the compute that gets done, gets inserted on most of the computers. But in terms of software and orchestration architecture, I required all these things in order to make this as robust and spins up as fast as possible. And we're even able to make this work on what are called spot instances on Amazon, which are much cheaper instances that Amazon makes available for you, but it has zero uptime guarantee, meaning that anytime any user wants to pay the full price for the node, Amazon can take it away from you, right? But we're able to make it work, like these computational workloads, by building in a lot of monitoring tools around, what Amazon thinks, is going to be taken away from you soon. And all this structure is built in there to be able to support that. If Amazon is going to terminate your machine soon, we take your current wave field and we say, oh, we're going to save as much as we can, and then we're just going to pack everything up, and then we'll evacuate this thing in a safe manner so that another machine, when it comes online, can sort of continue to work. And we also rejigger the architecture so that it doesn't need to sort of everything finish at the same time and start at the same time. We can have machines, if there's work to do, we can have machines start up, and if there's no more work to do, if you're waiting for other nodes to finish computing, that computer can just shut down and you are not paying for it anymore. So you're literally only paying for compute that you use. You are not paying to wait around for all the shots to finish, to get a gradient, to get an update, for all of that. Okay, so that actually enabled us, because there's a lot of flexibility built into when you can get compute, right, and how much compute you can get. We're able to do a lot of scenario testings. Okay, that's what this enabled us to do. So imagine having a cluster that today, because I have a large project to do, is a 10,000 machine cluster. And tomorrow, because I finished my parameter search, it's a 0 machine cluster and I pay no upkeep for it. Okay, so that's basically the dream, right? If you're on an individual team, if you're not like your IT department in a giant corporation and have many, many people that you're scheduling compute all the time. If you're just a team trying to run your project, that's like the dream scenario. And that's what running on AWS enabled us to do, because AWS is so big, it's basically the world's IT compute department. Effectively, for each individual user, it is going to look like an unlimited pool of compute that you can just sort of burst into. So that's what, in terms of the results that we get, what that means is that we can test many, many different things. And before, one of the large impediments is that if you want to test many, many things, and each run takes 3 or 4 days, on a very large number of nodes, a lot of times you're waiting for like a week for all that compute to become available to you. Well, on Amazon, we don't really need to wait. We could just say, oh, I don't know. So for this example, we have a water bottom that we have defined because there's a density contrast there. We don't know what that density contrast ratio is, and we actually don't know where to start defining that change in density contrast. Okay, we don't really have that great of an idea of what the water bottom behaves like. So what we actually did is we tried many different density contrast ratios, and we also tried shifting the water bottom up or down a bit, just in case there's miscalibration issues. And immediately we found one particular combination that just works much better. So down here, these are individual shot, all the trace correlations inside that shot, and we averaged them over them, and these are just percentages, right, of the trace correlation. And you can see this is what we actually started out with. This is what we would have used very happily to run off FWI, but because we're able to do these scenario testing, that is otherwise very difficult for the normal FWI process to give you. We're able to do essentially what's like a global search for these, and we vastly improved the tracing. And this is not really possible if you have a single cluster that you have to wait a whole week for things to start. You typically just want to try 2 or 3 things, and then once you're pretty sure, you're like, okay, we need to run production, like, you just let it go. Or here, we just said, we just want to try, 3 or 4 or 5 or 6, however many. And they all just run. So that is a huge quality of life improvement for not only us in terms of offering services, but also for the clients as well, because they sort of have an instant feedback to this. So that's the result when we iterate that good model up to 20 Hertz. And we're able to have the data that it simulated go from here to here. And you can see it has a very, very good match against our field data. Okay, so what this means all the way down the line is that we're able to much more faithfully match the data given the same amount of turnaround time. And what that basically means is that the more faithfully you match your data and the more accurate your model is, the more risk that you reduce during drilling. So that's the whole key. Given the same amount of turnaround time, right, we want the risk to be reduced as much as possible. We want as good a velocity model as possible before the inevitable deadline comes and drilling will just start no matter what you do, right? Before this time comes, you want to reduce your risk as much as possible.